Welcome to the Deep Dive. Today, we're looking at something fundamental, how our solar system, actually got put together.
Right. And the picture most people have is probably dust and gas clouds swirling around.
Yeah, just sort of clumping together over time, collisions, gravity doing its thing.
That's the standard accretion model, yep. Lots of little bits bumping into each other, eventually building up planets.
But the material we looked at today offers a really different perspective. It's called motion theory.
It is quite different. The core idea is that it's less about random particles in empty space and more about structured rhythmic motion, almost like patterns interacting.
Patterns, not particles. So like everything's connected through movement.
Kind of, yeah. And gravity, in this view, isn't really a force pulling things across empty space. It's more an effect of things moving towards greater synchronization.
Okay, hang on. So instead of gravity pulling dust together, it's like movements aligning, and that causes things to come together towards higher sync density, I think the source called it.
Exactly. Imagine the early sun setting up this really powerful rhythm, a kind of convergence field.
Right.
And within that field, different motion patterns are competing, essentially, trying to find stability.
So our mission in this deep dive is to unpack that the solar system's architecture, viewed through this lens of structured motion survival under sync convergence gradients. Bit of a mouthful.
It is, but the concept is key. Which motion patterns survive depends on how well they can hold together under that sync pressure.
So the planets aren't just accidental blobs, they're the winners of this cosmic motion competition.
That's the idea. Motion theory suggests the heavier, more, let's say, tightly organized motion systems, think dense, coherent loops of movement, they could stabilize closer to the sun.
Where the sync density was highest, like staying stable in strong currents.
Precisely. The closer to the sun, the more intense that synchronizing effect, that sync storm. Only the really robust patterns survive there.
Which brings us to the inner planets.
Mm-hmm.
Mercury, Venus, Earth, Mars. These are the high-density sync survivors.
That's how motion theory frames them. They had the structural integrity, the dense synchronized motion needed to withstand that inner solar system chaos.
And lighter stuff, less organized motion.
It would either get pulled into the sun or maybe flung further out. It couldn't maintain its structure in that high sync zone.
Okay, now Jupiter. The source uses some pretty dramatic language here, a gravitational resonance hammer, a sync wedge.
Yeah, it really emphasizes Jupiter's active role. In this theory, Jupiter's massive structured motion field basically disrupted the whole synchronization process just beyond Mars.
How so? Like stirring the pot.
Exactly like stirring the pot. It prevented smaller bodies from properly syncing up and forming another stable, rocky planet.
So that's the asteroid belt connection.
Yeah.
The debris from a planet Jupiter stopped from forming.
That's the implication in motion theory, yes. And it didn't just affect the asteroid belt. The theory suggests Jupiter's influence also sort of stunted Mars's growth and maybe even interfered with its atmosphere developing.
Wow, okay, so Jupiter wasn't just passively collecting gas, it was actively shaping the layout.
A major player in structuring the system, definitely. Then, as you go further out...
into the outer sync drift zones.
Right. Out there, the sun's synchronizing influence, that central rhythm, gets much weaker. The outward motion convergence, as the source puts it, is less powerful.
And that's why we see the gas giants, Jupiter, Saturn, and then the ice giants, Uranus and Neptune, because the conditions were different.
Exactly. Weaker sync means the motion patterns that stabilized were less dense, more spread out, cooler. You get these larger, less structured planets.
So it follows a principle. The farther from the sun, the weaker the sync, the looser the structure.
That's the core relationship proposed, yes.
This theory also flips some common ideas, doesn't it? Like it says temperature is more of a symptom, not the main driver.
Right. Temperature is seen as an effect of the structured motion dynamics rather than the cause of where planets form. And mass alone isn't the full story either.
It's about how that mass is organized, how the motion survives under pressure.
Precisely. It's motion survival under sync pressure. The planets, their orbits, their sizes, even atmospheres, they're all seen as effects of where stable, structured motion could persist. These zones of stability.
Not just random collisional outcomes.
Not in this view, no.
Right.
It's a much more ordered, structured process.
And there was that new principle mentioned, motion convergence sorting. How does that fit?
It sort of summarizes the overall dynamic. Think of the sun as the core convergence point. Heavier, more tightly synchronized motion systems naturally settle closer in.
While the lighter, looser stuff drifts outwards.
Or gets disrupted, yeah. It's
Yeah.
sorted by its ability to resonate and stabilize within that convergence field.
So the big takeaway here is that, according to motion theory, our solar system's structure, rocks in, gas out, isn't just luck of the draw.
Not at all. It's presented as a direct result of these structured motion dynamics, a record of which patterns survived those early sync storms.
It really makes you look at the planets differently, not just as objects, but as, well, the source called it a frozen echo of a cosmic motion battle.
It's a powerful image, isn't it? It reframes the whole system as a consequence of fundamental motion principles.
Definitely gives you something to think about. So, the final thought for you, our listener, is if this idea holds true for our solar system,
How might these same principles of structured motion, synchronization, and convergence be playing out elsewhere in the universe? What other cosmic structures might be echoes of similar motion battles?